This lecture is divided into 3 different parts. In the first part, we're going to go through a tutorial and implement a BCD to 7-segment decoder. This is very similar to what we did in a previous lecture where we implemented a curtain motor control unit. In the second part of the video, we're going to take a look at something called a 4-bit equity comparator, which compares 2 4-bit numbers. We're going to introduce to you formally the concept of hierarchical designs as well as functional blocks. And then in part 3, we're going to touch briefly on the concept of technology mapping, giving you some more practical tips. Before we get started, it is very important that we do a quick review on the systematic designing procedures so you don't forget. The systematic designing procedures are designed to be universally applicable, meaning that it can be applied to whatever situation where you want to design a combinational logic circuit. We have 5 different steps. Step 1, specification, which is usually provided to you as the problem that you're trying to solve. Step 2, formulation. You take your specification and derive the relationship between all of the input and output ports of the systems. This can be done in 2 different ways. In the previous lecture, we've shown you formulation directly using Boolean expressions because that was simpler for that particular example. In today's lecture, we're going to take a look at one example which uses truth table. Step 3 applies optimization so that you can minimize the number of logical gates as well as literals required in your Boolean expressions, thus simplifying the following steps, which is actually implementing the circuit. Step 4 deals with technology mapping. It is, first of all, take a look at what kind of technology or physical components you have at your disposal. This could be either completely physical or could be from a simulator. And then you take all of these components to transform the optimized Boolean expressions to the actual circuit or simulation. And then finally, we have verification, in which process you should try to verify the correctness of the final design, the correctness of the circuit that you have implemented, and check its functionality to see if it meets all of your specifications. So, let's jump right into the first example of this lecture, a BCD to 7-segment decoder. To understand exactly what we're trying to do, the first thing you need to understand is what exactly is an LED 7-segment display. The 7-segment display, it has the formulation on the right hand side. You will commonly find this kind of a display on stuff like digital watches as well as elevators. It is essentially using a combination, an array of LED strips to display numbers. As you can see on the right hand side, this is the common formulation of such a 7-segment display. You have different LEDs, LED A, LED B, LED C, D, E, F, G, as well as a decimal point. By lighting up different strips of these LEDs, you'll be able to display certain numbers. Now, it is specified in the international standard ISO organization that a 7-segment display should always be arranged in this particular order. Namely, the 7 segments are displayed as follows. You have segment A, B, C, D, E, F, G, always in this precise order, as well as the decimal point, which is optional. What we're going to do is we're going to design a control circuit for our 7-segment display, which is actually a valid component inside LogicWorks that we're going to use to test our implementation. So you already know what a BCD is. A BCD stands for binary coded decimal, which represents a decimal number, each digit using a 4-bit binary integer. So a BCD to 7-segment decoder essentially translates that BCD code to the actual control sequence for the 7-segment decoder. It takes a decimal digit in BCD, so let's assume it takes 4-bit integers represented with capital A, B, C, D, and you'll be required to generate the appropriate control signals for the display unit. In this case, we're going to denote them using the lowercase a, b, c, d, e, f, g for convenience. And that is essentially your specification. In your specification, you have 4 bits of input, A, B, C, D, and you have 7 bits of output, because we don't actually need a decimal point for this particular exercise. In step 2 formulation, we're going to transform this description of our circuit into actual truth table, in this case. Here we have created a table with all of the decimal numbers on the input side, as well as its BCD representation, A, B, C, D denoted. And then on the output side, we have shown you a graphical representation of what the output would look like. For example, for the decimal number 0, the input BCD sequence should be 0, 0, 0, 0, and the output should be the appropriate arrangement, so that A, B, C, D, E, F, only these parts of the LED are lit up. So the lowercase a, lowercase b, lowercase c, d, e, f are light up and outputting a positive signal. And G in this case would not be lit up, so it would receive a 0 value. For the sake of simplicity, if we don't write down the actual number, in the truth table it is considered 0. We proceed to number 1. For the decimal number 1, we have input A, B, C, D equals 0, 0, 0, 1, and then the output should be just B and C lit up. So the rest of them, A, D, E, F, G, should be 0. Proceed to number 2. You can see number 2, we have input 0, 0, 1, 0 and output A, B, D, E, G lit up. So C and F are zeros. Next up, we have 3, 0, 0, 1, 1. Similarly, A, B, C, D, G should be lit up. E, F should be zeros. Step 4, 0, 1, 0, 0. We should have B, C, F, G lit up, and A, D, and E outputting zeros. Continue all of these steps. I will skip the individual details to the end of the truth table. This is 5, and then 6, 7, 8, 9. And there we have it, all of the truth values that we actually care about so far. Now, theoretically, it is indeed possible to go and cover all of the 16 different combinations for A, B, C, D, but since we're only expecting BCD values in the input, the rest of the values for decimal value 10 all the way to 15 is not necessary. So we can consider them don't care conditions. So the next thing we're going to do is to take this truth table and perform optimization. And by doing that, we mean we want to convert the truth table into Boolean expressions. The exact method is going to be used over here is simply to take the sum of minterm for each and every one of the output points. So for example, A will have a sum of minterm 0, 2, 3, 5, 6, 7, 8, 9, and so on and so forth for B, C, D, E, F, G. After getting the sum of minterms, we will need to perform further simplification, for example, by using either K-map or binary identities. In this particular case, I've skipped ahead to show you the actual result of our optimization. but it is very important that you attempt at least to do it on your own first. Once you're done, let's move on to the next slide. Here's the result of your optimization. We have the Boolean expression of each and every one of the output ports. Again, this comes directly from the truth table by using K-map, or from the truth table to sum of minterms, and then using binary identities to obtain these. The next step we can do is to try to perform technology mapping. And in technology mapping, of course, we will need to understand what kind of technology is available to us. So in this particular case, if we implement each and every one of these terms individually, so for example, we implement not AC using a single AND gate, and then not ABD using another one, and so on and so forth. This would require a total of 27 different AND gates and 7 different OR gates. So this is actually quite a complex design, and instead of doing this, what we can do is we can use some shared components. You can notice that some of these some of these product terms, such as not B, not C, and not D, they actually occur quite a few different times. And then what we can do over here is we can share these the output of these of these AND gates. We implement, for example, not B, not C, and not D, and then this is denoted using the red rectangle over here, and then share the output of the same unit with the circuit that generates output A, C, D, and E. By doing that, we'll be using only 14 different AND gates and 7 different OR gates. So as you can see, even in technology mapping, you can actually make a difference by using different implementation philosophy to make your life a little bit easier. So in the next step, we're actually going to go into LogicWorks and try to implement this circuit. Again, it is highly recommended that you try to implement this on your own, side by side, as I'm doing it. We're actually going to use a set of different input and output devices. So you'll notice that our input is actually comes in BCD. And for this particular case, it's going to take in binary values from 0 all the way to 9. What we have at our disposal previously is only the binary switches, which is going to take up quite a few different ports, 4 ports to be more exact. So what we can do over here in this particular case is we can go into our libraries. This is located in Simulation IO, and we can actually get something called a hexadecimal keyboard. And you'll notice that you actually have 2 different kinds of hexadecimal keyboard. One is, let me drag this out a little bit. One is with an extra pin at the bottom. The pin's name is called SDB. We do not need this. What we need is the hexadecimal keyboard without STB. So let's drag that out, and this will be our input. In this particular case, or example, I should say, what we're going to do is we're going to, again, drag out a little bit the individual wires. What you can choose to do is to give them individual names, such as A, B, C, D. As we said before, it is very important that you label your input and outputs. The next thing we can do is we can start getting ourselves all of the output symbols. For the output symbols, what we can do is we can directly get from the Simulation IO library a 7-segment display. As you can see, we do have quite a few different selections of 7-segment displays. For this case, I think I'll just go with my favorite color, which is, okay, they don't actually seem to have burgundy, so I'll choose red in this particular case. I drag it out and place it over here. And to my specific liking, again, I want my A to be on top, so I can flip this component vertically. And then, because this is the output, I want all of its pins to be on the left, facing the input ports. I right-click and then flip it horizontally. So that right now I have all of my output ports facing the right direction, and they're labeled A all the way to G, all of them lowercase. And the way this 7-segment display works is we can use binary switches to demonstrate how it roughly works. Okay, I probably need to flip this one as well. Let's flip it horizontally so it's facing the right direction. So the moment, for example, I plug this into A and flip it on, you'll see that the segment A has been lit up. So this is exactly how I receive signal. If the signal is 1, then the corresponding segment will be lit up. If you turn into 0, it will disappear. And something that we already know is we don't actually need the dot over here. So what we can do is we can feed the dot with a constant value. And to be able to do that, what we can do is we can get something called a digital ground. The digital ground can be simply sought over here. And here it is. The digital ground, once connected, will always give you a 0 value. As you can see, the dot has disappeared, and if you use a binary probe to examine its value, it will be in the low voltage area, which is a 0. So let's delete all of this and then concentrate on finishing our implementation. First of all, let's implement the shared components, the shared product terms. To be able to do that, first of all, let's do not B, not C, not D. In this particular case, because B, C, D are all inverted, we can use an AND gate with 3 inverted inputs. You can actually see which ones are inverted by looking at the hollow dot. So in this case, all of them are inverted. We're going to need to plug this into B, C, and D. Let's try to make it pretty over here so that it's easy to see. And here we go, B, C, and D. What we also need to figure out is a series of receiving end on the output side. So let's take a look at A. A is going to need 4 different OR terms connected together. So let's get some ORs. This is a 4-input OR gate. We can simply use it here. This is for A. B is also going to need a 4-input OR gate, so this is B. Let's connect them briefly. C requires also 4-input OR gate. D requires 5, so let's drag out a 5-input OR gate. Let's make it pretty over here. A, B, C, D. Always check your connections. For E, we need 2 of them, so let's just do a 2-input OR gate. Let's drag this a little bit to the right so it doesn't get in the way. I think it's still going to get in the way, so let's make this whole thing a little bit to the right so there's more space. And then for F, we need 4 and 4 for G. Okay. Again, if you're feeling a little bit confused, you can always give them names. But in this case, because they're all named capital A, small a, I'm afraid the system would probably go into panic by seeing names like that. So we can also use text over here, the text box, to draw names. So this particular one, let's call it small a, small b, small c, d, e, f, g. The text box names will appear as black instead of the usual magenta color for wire names. Now let's continue to see which one of the components actually uses not B, not C, not D. This will include A, so let's do a wire connected to A over here. This is also used by C, so let's do that. D is also using this component, and E. Let's adjust it a little bit so that it looks a little bit better. So that is your not B, not C, not D. Next up, let's do something simple. Let's do not A, not C, not D. So let's copy and paste this thing around. Not A, can be over here. Not C, let's drag out C over here. This is C. And D. Always check your connections. This is not A, not B, sorry, not C, and not D. And this particular one is used by D, sorry, output B, and output F. Again, this particular one is not connected. That's why it's important to check connections. Okay, now it's connected. And next up, let's do this is connected to F. Okay. Again, always check connections to see that they're actually connected. Next up, let's do A, not B, not C. In this case, A, not B, not C has 2 inverted, 1 not inverted. So let's try to find that. Search for the AND gate, 2 invert, place it, sorry, 3 input AND gate, 2 inverted, place it over here. And in this one, A is not inverted, so let's connect that with the uninverted component, and then not B and not C. This is B, connect, and then C is on this wire, so let's connect that. This one will be plugged into quite a lot of different components, so let's make it a little bit closer. This is connected to A, as well as B, C, D, not E, but F and G. And next up, let's implement not A, C, not D. Not A, C, not D will require, again, 2 inverts and 1 not inverted. Let's place it over here. This one will need to be connected to A, so let's do that. Wait, sorry, my mistake. A should be inverted in this particular case. The one not inverted is C, so let's connect this to C. The ones inverted are not A, not D. This is again A, this is D. Always check your connections to make sure you're not making mistakes. And then not A, C, not D should be connected to D, E, and G output. Let's make it closer. D, E, and G. Now the circuit is already starting to look a little bit complex, and if you think this is the most complicated circuit you're going to encounter in this course, well, you want to think again. This is not even close. But before we get into that, let's continue implementing this. There's a couple of shared ones we need to do. Not A, not B, C, for example. Let's do that. Not A, not B, C. So this one be not A, and then not B. This is not B. C is on this wire, and it should be connected like that. And again, this is not A, not B, C. Not A, not B, C should be connected to D and G. Just like every other course in computing science, patience is a good virtue to have over here. Now let's see if there's any other components that will be shared but we haven't implemented. Okay, I can see this is not A, not C, not D. I think, have we done not A, B, C? I think we have. What's the last one? Oh, okay. Wait, have we done D, E, G? D, E, G is covered. Not A, not B, C. Did we do not A, not B, C? I think we did. I think this is not A, not B, C. What about not? Okay, we need to do not A, B, not C. Let's try to copy that. This should be connected to A, so it's not A, and then not C, and this should be plugged into B. Let's do that. Again, this is not A, B, not C, which is showing up on the Boolean expressions as orange, and this one should be plugged into F and G. Okay, the rest of the terms we'll have to implement individually, so let's do it from A. So for output A, over here we also need to implement not A, C. We can accomplish that using an AND gate with one invert. This is A. Over here, let's drag this thing out a little bit so it's easier to see. This is not A. And then we also need a C. C is on this wire, so we connect it here. This is C. And not a C is plugged into output A. Next up, we have not A, B, D. We need 3 input AND gate with 1 invert, so it's not A, B, D. This is not A, and then we need B and D. This is B and D. Always check your connections and then connect it to A. Let's make it a little bit tighter so we have more space. Actually, let's move this whole thing up a little bit because we want space for B and C as well, and they would require more components. Output B would require not A, not B, so that's 2 input, both inverted. This is not A. Let's connect it with A. And B. This is B, so let's connect. And plug this into B over here. Let's move this entire wire a little bit to the left so it's easier to separate them out. Circuit diagrams are always like this, they are complex. Sometimes quite nasty, but we try to make them nice. Next up we have not A, C, D. So first of all, not A. C is on this wire. D is on this wire. And this is connected to B. And right now we have the inputs for output A and output B completed. Let's move these upwards a little bit more and then do C. For C we need 2 extra components, not A, B. This is B. This is connected to C. I think getting a little bit crowded over here, but we'll manage. And not a D. This is A, this is D. It's connected to C over here. Make sure it doesn't overlap with any of the other wires so as to create unwanted connections. The graphics is glitching a little bit, scrolling down and up, and it will be resolved. Now let's turn to the back over here to implement C is completed. Let's do D. What does D need? Not A, not C, B and D. So let's do a 4 input AND gate with 2 inverts. Again, this is not A. So not A, not C. Okay, not A, not C. Which one is C? Wait, this is A, B, C is this one. Okay, this is C and B and D. Check your connections as always. And now we can plug this in to D. Again, you can drag this wire across different places. Just make sure they don't form a solid dot. If they do form a solid dot, you will need to remove it and redo the connection again, which takes time. Or you can use Ctrl Z or Command Z, depending on whether your system is Windows or not. I map my keys, so I'm using Command. Now I think there's only one left, which is F. For F we need not A, B, not D, so let's do that. 3 input AND gate, 2 inverted. This is A, so let's negate it. We need one for B, which is not inverted. Okay, check your connections, and then finally not D. This is not D, it's connected. and connect this final little bugger to F. And we will have completed our implementation. Let's move the timing diagram, minimize it a little bit, and examine our circuit. It's quite a mess, but sometimes in circuit design this is necessity. What we can do now is we will need to go into step 5 by verifying our implementation. Input 0 will output to you a 0. Input 1, that's 1. 2 is 2. 3 is 3. 4 is 4. 5 is 5. 6, 7, 8, 9. And the rest of them we don't care, because for us this is a 7-segment display control circuit by only taking BCD as input. So A, B, C, D, E, F values will not exist in BCD. As you can see, they actually don't give out anything right now. So that is actually the whole tutorial for how to design a BCD to 7-segment display controller. And again, please try to do this in your own time and try to make it well, as clean as possible. I can realize that it's not actually very easy to make this tidier, but one should try one's best and make sure you're doing things right. And again, always check your connections whenever you make a new connection, and always check your final implementation once you're done with it by doing verifications. Oh, and of course, please remember to save all of your circuit. Go to File and Save Circuit. Thank you very much.